So, hello everyone. So, good afternoon, students. So, am I visible and audible to you? Just let me know in the chat box if I'm visible and audible to you. Yes, thank you so much, students. Okay. So, good afternoon again to all. Today we are going to discuss about the coordination compounds questions. Okay. So, my name is Anandi, and let's start with the first question for today's class. And in today's session, we are going to cover the given four topics which you can see on the screen. They are Werner's theory, nomenclature, and isomerism, and valence bond theory. Okay. So, crystal field theory and the color of the coordination compounds and metal carbonyls, they are not discussed today. So, we are going to see questions from these four topics. Okay. So, let's start with the first question for today. So, I hope you all can see the question on the screen. So, the type of isomerism exhibited by compounds. So, three different compounds are given to you, and you have to find out the isomerism exhibited by these three compounds, and also you have to find out the value of coordination number of the central metal ion in all these compounds. Okay, so find out the coordination number as well as the isomerism. Okay, I'll give you some around 30 to 45 seconds to solve this question. So just try to do the question and let me know the answer in the chat. Okay. Has anyone got the answer? Has anyone got the answer? So what is the type of isomerism exhibited here? So isomerism is classified into two. They are structural isomerism and stereoisomerism, right? Under structural isomerism, we have linkage isomerism, coordination isomerism, and ionization isomerism and solvate isomerism. So you can observe the given three compounds here. So what is the difference between these three compounds? So in the first compound, you can see actually here we should have a bracket. Okay. So we have chromium metal which is attached with the sixth aqua water ligand and 3 chlorine is outside, and here also you have to get the bracket here. Okay, that should not be two here, it is only one. And one H2O is put out and one chlorine is taken in, okay, inside the complex. And here the third complex, if you see, two chlorines are taken inside and two water molecules taken outside from the 6H2O. Okay, so the number of H2O molecules which is present inside the coordination entity as ligand differs. Got it? So the isomerism is solvate isomerism. So isomerism is called as solvate isomerism. Okay, and you can see the coordination number in all these cases. So what is the coordination number? The number of donor sites, the number of donating site attached to the metal ion is called as coordination number. So in the first complex, you can see there are 6 ligands attached to chromium. In the second case also 5 H2O molecule and 1 Cl. So totally 6. And in case of third complex, there are 4 H2O and 2 Cl. So totally 6. So the coordination number of the given three complexes 6. Okay. So option B will be the correct answer for this question. Clear? Students, if you have any doubt, you can put it in the chat box. Is the question clear to you? For JNP, Nissamabad students, is the question clear to you? To all of you? If the question is clear to you, just put S in the chat box so that I can move on to the next question. Shall I move on with question number 2, students? Yes or no? Yeah. Okay, I'll move on to next question. The homoleptic complex from the following complexes is. So four options are given to you. So we do have two different types of complex. One is called as homoleptic and the other one is called as heteroleptic. Okay. So what is the difference? So homo means we all know that it is same. Homo means same. If you have the same ligand present inside the coordination entity as ligand, so it is called as homoleptic. And if you have different types of ligands attached to the metal atom, then the given complex is heteroleptic. Okay. So let's check with the first option. We have diamine chlorido So diamine means it is NH3 twice and chlorido it is Cl and nitrito N is NO2, right? And the metal atom is platinum. Metal atom is platinum. Platinum is in +2 oxidation state. So amine is neutral and Cl is -1 and NO2 also has -1 charge. So the oxidation state of platinum is +2. So this is the complex. And coming to option B, it is pentaamine. It is NH3 5 times carbonato, the CO3 and cobalt chloride. So chloride is out. So carbonato has 3 minus charge and 2 minus. And here if I put only one chloride outside, it will be +3 for cobalt. Okay. And coming to the third complex, it is triamine. Triamine means it is NH3 3 times and triaqua. Triaqua is H2O 3 times and chromium is the central metal atom. Chloride is out. Now both amine and aqua, they are neutral ligand, right? But the oxidation you can see it is 3. So what I have to do? I have to put 3 out. Okay. And coming to option D, it is potassium trioxalato. Oxalate ligand is OH or C2O4 you can put trioxalato aluminate. Aluminium is a central metal. And each oxalate has -2 charge. So here 3 into -2 is -6. But the oxidation state is +3. So I have to put the 3 potassium out. So that I will get the oxidation state of aluminium as +3. Okay, that is +3 for potassium, X for aluminium, and 3 into -2 is -6 equal to 0. X is equal to 6 minus 3, which is equal to +. Okay. So these are the complexes for the given names. And just check which complex is having only one type of ligand in it. So in case of the first option, we have 3 types of ligand. One is amine and the other one is chloro and the third one is nitro. In case of complex 2, there are 2 types of ligand attached to it. In option C also same. But in case of option D, we have only one type of ligand which is oxalate. Okay, oxalate is nothing but C2O4 2 minus. Okay. So that is the homoleptic complex and the remaining 3 complexes are heteroleptic. So option D is the correct answer for this question. Clear? Fine. Let's move on to next question. So given below are 2 statements. One is assertion and the other one is reason. So we have to find out the correct statement. The assertion is the spin-only magnetic moment value of FeCN6 3 minus is 1.74 Bohr magnet. Whereas for iron aqua complex is 5.92 Bohr magnet. In both the complexes, iron is in +3 oxidation. So just take 30 minutes to solve this question, 30 seconds to solve this question, and try to put the answer in the chat box. Okay? JNV Nissamabad, I hope you guys are listening to the class. So try for the answer for this particular question and give me the answer in the chat box within 30 seconds to 45 seconds. Okay? Just tell me whether the given assertion is correct or not. Tell me whether the given assertion is correct or not. Okay. So the spin only magnetic moment value for the given complex is 1.74 Bohr magneton, they are saying. So you can see the oxidation state of iron in this case is, yes, for each cyanide it is -1. So 6 cyanide we are having, so -6, which is equal to -3. So X is equal to +3. Okay. Iron is in +3 oxidation state. Okay. If iron is in +3 oxidation state, then the configuration would be 3d5 and 4 is 0. Okay. Iron has 5 electrons in its d orbital. Let me draw all the 5 electrons here. So this is a 3d orbital. 1, 2, 3, 4, 5 electrons are there. Now you can see the cyanide is a strong field ligand. So what happens? Pairing of electrons occurs. So the electrons are now going to get paired. Now after pairing occurs, we are going to get a configuration like this. 2 electrons in first orbital and 2 in second, and only 1 in third. Okay, clear? So what is happening here? We have 1 unpaired electron in d orbital. If the number of unpaired electron is equal to 1, then the magnetic moment will be 1.74, right? So this is what we have studied. So the given magnetic moment value for the complex is correct. And coming to the second complex, which is hexa aqua, here also you can see the iron is taken as X and the water is taken as neutral ligand, so 0. Oxidation charge on the complex is +3. So the oxidation state of the iron is +3. So same configuration. But H2O is a weak field ligand. H2O is a weak field ligand. So pairing does not occur. So from this configuration, pairing does not occur. So the number of unpaired electron will be equal to 5. So the magnetic moment will also be 5.92 Bohr magneton. Okay. So assertion is correct. Assertion is correct. And the reason you see both the complexes contains +3 oxidation state of iron, that is also correct. But just check whether the given reason is correct for the assertion. Both are having different magnetic moment. Okay, that is not due to the same oxidation state of iron. Both are having different magnetic moment due to the different ligand field. Okay, cyanide is a strong field ligand and H2O is a weak field ligand. And because of that purpose only, both are having the different magnetic moment value. Not because of the same oxidation state of iron. Okay, so what would be the correct answer for this? Both assertion and reason are true, but R is not the correct explanation of E. Okay, so option D is the correct answer for this question. Clear? Fine. So let's move on with the question number 4. Which complex is most stable? Which complex is most stable? 4 different complexes are given to you. You have to tell me which complex is most stable. Just observe the complexes. Take your time and try to get the answer. Try to get the answer. Okay, let's discuss. So in the first complex, you can see NH3 and NO3 is attached as ligand. Both are unidentate ligand or monodentate ligand. Okay, both the ligands are monodentate ligand. And coming to option B, we have 2 different types of ligand. Fluoro is monodentate, but ethylene diamine is a didentate ligand or bidentate ligand. Okay, bidentate or didentate. And coming to option C, we have NH3 as ligand, which is monodentate ligand. Okay. Coming to option D, we have 4 amine ligand, 1 H2 and 1 Br. all the three ligands are monodentate. All the three ligands are monodentate ligands. Okay. So we all know that bidentate ligand has chelation property, right? What is meant by chelation? Chelation means ring formation. So the ring forming ability containing ligand is ethylene diamine, I mean a didentate or bidentate ligand. Okay. So if a ring is formed between the metal atom and the ligand, for example, in case of option B, I'll tell you the cobalt is attached. It is an octahedral complex. You can see the coordination number is 4 since ethylene diamine is the bidentate ligand. So let me draw the cis isomer. Okay. Ethylene diamine is NH2, CH2, CH2, and NH2. Right. This is the first ethylene diamine. And let me take this is the second ethylene diamine. And these two are fluoro. Got it? So it is forming a ring. Ethylene diamine is forming you can see it is forming a 5-membered ring. Got it? So the ring forming ability containing ligands are more stable in the aqueous solution. Okay. So they are more stable compared to monodentate. If it is monodentate, once this bond gets broken down into the solution, it goes into the solution. But in case of bidentate, we have two bonds, right? We have to break these two bonds. Then only they will go into the solution. Means they will become unstable. Got it? So the chelation ability containing ligands are more stable. Since ethylene diamine is a chelating ligand, complex B is most stable among the given 4 options. Okay. So option B is the correct answer for this question. Got it? All the polydentate ligands, not only ethylene diamine, oxalate is a bidentate ligand, and EDTA4 minus, ethylene diamine tetraacetate, which is a hexadentate ligand. So all these ligands, they are stable. They are most stable compared to monodentate containing system. Got it? So let's move on to question number 5. Yeah. The IUPAC name of K3CO C2O4 trices. What is C2O4? C2O4 is the oxalate. C2O4 is oxalate. Just before few minutes only we have discussed. Right? So we have to find out the IUPAC. So to find out the IUPAC name, what we have to do? We have some set of rules to name the compound. And rule number 1 is you have to name the cation first. Okay. Here you can see the complex starts with potassium, in which that is a cation. Potassium is the cation. So that has to be named first. So in all the 4 options, you can see potassium is in the first position. That is okay. Then what you have to do? You have to name the anion, which is the coordination sphere for us here. Okay. So for that, start from the ligand. Ligand is oxalate. And how many oxalate we are having? We have 3 oxalate. So it is trioxalato. It is trioxalato. So we should not use tris. Where we use tris or bis? We use tris or bis only if a ligand contains numbers. Okay, if a ligand contains numbers, for example, in case of ethylene diamine, the IUPAC name of ethylene diamine is ethane 1,2 diamine. Okay, now you can see here that the name of the ligand contains numbers. So in this case, if we have En twice, then in the name what you have to do? We have to put bis. Bis ethane 1,2 diamine, like that we have to write because it includes numbers. Whereas this oxalate ligand doesn't contain number in its IUPAC name. Okay, so you should not use tris. You have to use tri. So it is potassium trioxalato, and now the differences between option C and D, which is correct. It is cobaltate or cobalt. So in one of the IUPAC rules of coordination compounds, you might have come across a particular thing like if a coordination entity is the anion, okay, if the coordination entity is the anion, then you have to end the central metal atom name with ATE. Okay, if the complex is neutral, or if the complex is a cation. The complex is neutral, or if the complex is cation, then what you have to do? You have to end the central metal atom name as such. If it is cobalt, you have to put cobalt. If it is nickel, you have to put nickel. But if the complex is anion, if it is anionic in the system, example, then you have to name the central metal atom by using a suffix called ATE. Okay. So you can see potassium is the cation here and the coordination entity is the anion. So the complex is anionic in nature. So you have to end the central metal atom name with ATE. So the name will be potassium trioxalato cobaltate, and the oxidation state is 3. In all the options here it is given in 3 only, but we can also calculate. So let me take this cobalt as X, and for each potassium 1 plus charge, so this is plus 3 plus X, and for each oxalate it is minus 2. I have the 3 oxalate, so 3 into minus 2 is minus 6, which is equal to 0, and X is equal to plus 3. Okay, so the correct answer for this question is option C. Got it? Fine. Coming to question number 6. It is match the following. Match list 1 with list 2. The complexes are given to you in list 1 and the types of isomerism is given to you in list 2. We have to just match it. It is one of the very easiest questions, right? Just try to do it. You can get the answer within 5 to 10 seconds for this. So just see option 1. Option, the first complex you see. So we have NO2 and ONO. So what is this? It is an example for linkage isomerism. The atom which is attached to the central metal atom. The atom which is attached to the central metal atom differs. So in the first complex, to the cobalt, N is attached from nitro, and in the second complex, to the cobalt, oxygen is attached. So you can see the linked atom is different. So it is an example for linkage isomerism. So A goes to 3. A goes to 3. Okay. And in option B, you can see 2 coordination entities. 2 coordination, one is a cation and the other one is the anion. So the interchange of ligands between the 2 metal atoms leads to this. So what is this? It is an example for coordination isomerism. It is an example for coordination isomerism. So B goes to 2. And coming to the next compound. So from in the first compound, SO4 is given, bromine is outside, and in the second complex, bromine is inside and SO4 sulfate is outside. So we will get different ions in the solution if we treat these 2 compounds in AgNO3 or some other salts. Okay, so these 2 compounds produces different ions when they put into the solution. So they are ionization isomerism. So they are ionization isomers. So C goes to 1. And coming to the last one, you can see there are different H2O molecules present inside the complex as ligand. So it is an example for solvate isomer. So A3, B2, C1 and D4. Where it is given in option D. That is the correct answer. Okay. Clear? Fine. That's such an easy question for you. And coming to next question. Which of the following complex is octahedral, diamagnetic, and the most stable bond? You have to use the valence bond theory to solve this complex. So the complex should be octahedral. Octahedral means it should have the coordination number of 6. So let's check. So here in the first complex, the coordination number is 6. Second complex also it is 6. Third also the same, and fourth also the same. So the coordination number is same for all. Means they are octahedral in nature. Now we have to check with the magnetic property. We have to check with the magnetic property. Okay. So we have 2 different magnetic magnetic nature, one is paramagnetic and the other one is diamagnetic. Mostly, all the weak field ligands containing complexes are paramagnetic in nature. So, who are the weak field ligands? Mostly the weak field ligands are Cl, all the halogens, Cl minus, Br minus, and H2O. All these are weak field ligands. So, they form paramagnetic complexes. Okay. So, strong field ligands, they'll form strong field ligand in the sense carbon monoxide, carbonyl, Cn minus. Okay. So, they will form diamagnetic complexes. So from this we can eliminate some options, right? And NH3 is also weak, strong field ligand only. So in the first complex you can see Cl is present and it will form paramagnetic, so it cannot be the answer. And in the second complex H2O is there, weak field, so it cannot be the answer. Whereas in case of option C and D, we have strong field ligand. Okay, we have strong field ligand. But let's check one by one. So let me start with the complex C. Let me take the oxidation number first. The oxidation number for cobalt here is +3 because potassium takes +3 and minus 6, 0. So from this X is equal to +3. Now X is in +3 oxidation state. That is cobalt is in +3 oxidation state. So the normal configuration of cobalt is 3d7 and 4s2. Now if 3 electrons are removed, what is the configuration? 3d6 and 4s0, right? Now in the d orbital, we have 6 electrons. Now since I've told you this cyanide is a strong field ligand, electrons are now going to get paired up. Okay, electrons will pair up and there will be no unpaired electron in the system. N will be equal to 0. If N is equal to 0, magnetic moment is going to be equal to 0. So the system is diamagnetic. Okay. So coming to nickel, the oxidation state of nickel is yes. NH3 is neutral ligand, so 0. And for each chloride, it is -1. So -2 equal to 0. And X is equal to +2. Okay. So for the nickel is in 2 + 3. So it is 3d8 and 4s0. 3d8 and 4s0 configuration. So how many electrons are there in d orbital? There are 8 electrons. Now, if I pair this electron, if these 2 electrons are getting paired, then we are left with one d orbital, one empty d orbital if this electron gets paired. Okay. And the next empty orbital will be S. And the remaining orbitals are P. P3 we have P. And the next one will be, this will be your 4D and one empty from 4D. We don't have such kind of geometry or hybridization, right? DsP3D kind of hybridization is not there. Such kind of thing is not possible. Got it? We do have only 2 different types for octahedral. One is D2sp3 hybridization and the other one is sp3d2 hybridization. Got it? So, for this particular reason, nickel is an exception. Nickel, even though it has a strong field ligand attached to it, which is NH3, the electrons, the unpaired electrons of nickel will not get paired up. Okay, so this pairing will not occur. So we are left with 2 unpaired electrons here in the system. If the unpaired electrons are equal to 2, then the system is paramagnetic in nature. Okay, system is paramagnetic in nature. So the only diamagnetic complex among the 4 given options is answer 3. Answer is option 3. Okay, and that is the most stable complex. Clear? Any doubt? Hi, Visakhapatnam students. Good afternoon. Good afternoon to all. So I'll go on to question number 8. Okay. If you're having any doubt, just put it in the chat box. I'll explain you again. Okay. I'll move on to the next question, which is said, we are asked to find out the IUPAC name of the complex. IUPAC name of the given complexes. This is your previous year NEET question. Okay. 2022 NEET question it is. So you have to find out the IUPAC name. So the given complex is an example for coordination isomerism. Ligands coordination compound it is. First is the cation and the second is the anion. Which we have two coordination entity. Just try the name for this and put it in the chat box. Both contain silver metal as the central metal atom. And mostly silver will be more stable in +1 oxidation state. Okay. The first will be the cation and the second one is the anion. The oxidation state of silver and the cation is +1. You can see the H2O is a neutral ligand. X plus 0 is +1. +1. And for this silver, cyanide has -2, which is equal to -1. So from this X is equal to +1. So both the silver are having same oxidation. Okay. Now what we have to do? So I told you if the complex is cationic or neutral in nature, you have to end the central metal name as such. So it is diaqua silver 1. Okay. And if the complex is anionic in nature, you have to end the central metal atom name with the suffix ate. Right. So it is dicyanide-argentate. For silver, we have to use argentate if the complex is anionic in nature. Got it? So the correct answer will be diaqua silver 1, dicyanide-argentate 1. Okay? Option D will be the correct answer. For cationic, we have to use silver. Silver, no change in it. And it is anionic, you have to use argentate. For gold, we are using orate, right? So like that for silver, you have to use argentate. So I'll move on to question number 9 then. The octahedral diamagnetic low spin complex among the following is the octahedral diamagnetic. Octahedral means I told you the oxidation, the coordination number will be 6, right? So in first option we have 6, second we have 4, that cannot be the answer. In third also 6 and fourth also 6. Diamagnetic. What is meant by diamagnetism? I told you, right? In case of strong field ligands, the electrons will get paired up and the complex will be diamagnetic. In option A, you can see the ligand is NH3 and the NH3 is a strong field ligand. And in option B, we have Cl minus chloride. In option C, also chloride. Option D also contains halogen, which is fluoride. So these three complexes have weak field ligands in it. If you're having a weak field ligand present inside the system as ligand, then in most of the cases, the complex will be paramagnetic in nature. Got it? So the one which is diamagnetic in nature is the complex containing NH3 as ligand. So option A will be the correct answer. You can find out the answer by using valence bond theory also by drawing the boxes and pairing. Okay, you can do that way also. So this is one of the kind of trick. If strong field ligand is there, diamagnetic, weak field means it is paramagnetic. Just the strong field, weak field list you have to memorize and that exception is observed only for nickel. So these things alone just keep in your mind and solve the questions. Okay. You don't have to waste your time by drawing the boxes in your exams. Okay. Now next I'll move on to question number 10. The order of energy observed which is responsible for the color of the complexes. So you can try for this. Three complexes are given to you. They are asked us to find out the order of energy observed. So here we have to use the same strong field, weak field ligand concept only. If the system contains strong field ligand, then the absorption of energy will be more. Energy getting absorbed is very more. Okay. If you are having a weak field ligand, then energy absorbed will be very less. So just apply this concept and try to get the answer. So we should know whether we know that H2O is the weak field ligand, right? And ethylene diamine is a strong field ligand. Ethylene diamine is your strong field ligand. So now you can get the answer for this question, I think. In the first complex A, we have 2 strong field ligand. In case of B, only 1. In case of C, we have 3 ethylene diamine. So more number of strong field ligands are given in compound C. So compound C only absorbs the maximum amount of energy. Okay, so it requires maximum amount of energy. Then the complex contains 2 ethylene diamine amine will absorb more energy, right? So it is option compound A and lastly compound B. So CAB 3, 2, 1. Okay. So option C will be the correct answer. Clear, students? Yeah. Now we're coming to question number 11. Question number 11 is very, very easy. Ethylene diamine tetraacetate ion is EDTA ion is. You have to find out the denticity. That's it. Very easy. Straightforward question from your book, right? EDTA 4 minus is a which ligand? Can you guess? JNV Nizamabad and JNV Visakhapatnam. Can you guess for the answer? Very, very, very easy question for you guys. Can you guys guess the answer? Any one of you? Or the students who are watching from YouTube, you can also give me the answer. Option B. Very good, Visakhapatnam students. Good, good. It is a hexadentate ligand. That's great. It is a hexadentate. Let me draw the structure of EDTA for you. So what is ethylene diamine? It is CH2, CH2 and NH2, NH2, right? This is ethylene diamine. So in ethylene diamine, all the 4 hydrogens are replaced by acetate ion. In acetate, you have to remove one hydrogen and connect it. So this is your ethylene diamine tetraacetate. Ethylene diamine tetraacetate. So you can see nitrogen is also having lone pair of electrons. So how many donor sites are here? So this ligand contains 1, 2, 3, 4, 5, 6. Mostly the negative charge containing center and the lone pair containing center, they will act as a donor site, right? No? So we have 6 donating site here. So it is a hexadentate ligand. For one ligand, you are having 6 donor sites. So it is a hexadentate ligand with 4 oxygen and 2 nitrogen donor atoms. So option B will be the correct answer for this. Yeah. Good. Let's move on to question number 12. The correct number of unpaired electrons. The correct order of the number of unpaired electrons in the given complexes is. Just find out the n value. To find out the n value, you need to find out the oxidation number. That's all. So what is the oxidation number of iron? Can you guys try for this? Can you guys try for this? I'll also try along with you. If you have get the answer before me, we can put it in the chat box. Okay. So the oxidation state of iron here is X minus 6 minus 3. X is equal to plus 3. And cyanide is a weak field ligand. Strong field ligand. So now iron 3 plus is having 3d5 and 4 is 0 configuration. 3d5 and 4 is 0 configuration. Okay. Now what happens? This is your 3d orbital, and among the 5 electrons, 2 will get paired and I will have only one electron, one unpaired electron here. Number of unpaired electron in the first case is n value in the first case is 1. Now coming to the second complex, oxidation state is again +3, but F is a weak field ligand. If it is a weak field ligand, the 5 unpaired electron remains as such, right? So the number of unpaired electron will be 5. Then coming to cobalt, cobalt is also in +3 oxidation state, but the configuration for cobalt 3 plus is 3d6 and 4 is 0. Because the cobalt neutral cobalt configuration is 3d7 and 4 is 2, right? By removing the 3 electrons, we get this type of configuration. And cobalt is having 6 d electrons. Okay. And this fluoride, you can see it is a weak field ligand, so the electrons are not going to get paired up. So 4 electrons, 4 unpaired electrons are there for the complex. 4 unpaired electrons. And coming to the next oxalate, you can see that chromium. Chromium is in +3 oxidation state. The configuration for chromium 3 plus is 3d3 and 4 is 0. Okay, 3d3 and 4 is 0. So how many unpaired electrons I have? Oxalate is a weak field, so I have 3 unpaired electrons. So the answer is 3. Then coming to nickel, you can see the complex is neutral in nature. So the oxidation state of nickel is 0. Oxidation state of nickel is 0. So the configuration will be 3d8 and 4 is 2 for nickel. Let me draw the 3d orbital first. Then on putting the 8 electrons in it, will give you this kind of configuration, and 4 is 2 I'm having, right? And this carbon monoxide, carbonyl ligand is a strong field ligand. So what happens? So always for hybridization, s orbitals are required. So the 2 electrons which are there in the s orbital, they will move on to its nearest 3d orbital. So 2 electrons will fall into the 3d orbital. Now 3d orbital has how many electrons? 10 electrons in it. So no unpaired electrons are there. So the number of unpaired electrons in compound E is 0. So now you can find out the increasing order, right? It is 0 first, which is compound E, then your compound A, then D, C, and B. So option is the correct answer. Option D is the correct answer. Okay, option D is the correct answer. So I hope you all can able to find out the oxidation state of the given atom by seeing the ligands. Right? If you're having any doubt in it, just ask me, I'll explain you. For oxalate, you have to put -2 for each oxalate. And for each fluoride ion, you have to give -1. Carbonyl is a neutral ligand, so 0. And for cyanide, it is -1. Clear? Yeah, I hope it is clear. We'll move on with one more question. Question number 13. Match list 1 with 2. The complex is given to you in list 1 and its magnetic moment values are given to you in list 2. So try for the answer. Just find out the number oxidation state first. By finding out the oxidation state, you will get to know the number of unpaired electrons present in it by seeing the ligands. And from the number of unpaired electrons, you can straight away get the magnetic moment value. If the number of unpaired electron is 4, then the value will be in 4 point something. If the number of unpaired electron is equal to 1, then your magnetic moment will be 1.73. So these are the fixed values, right? So just try to find out the n value. So for compound A, what do you get for compound A? How many unpaired electrons for compound A? Iron is in +3 oxidation state with the strong field ligand in it. With strong field. +3 contains 5 electrons, and with the strong field, they are going to get paired, and only one unpaired electron is going to be present there in the system. So n value is equal to 1. So A goes to 4. 1.73 will be the magnetic moment. So A goes to 4. Then coming to the second complex, the oxidation state of iron is again +3 since water is a neutral ligand and it is a weak field ligand. So in case of weak field ligand, all the d5 electrons, they are not going to get paired with each other, so it is going to be 5. So the answer will be 5.92. Okay, B goes to 1. And in case of option C, you can find that the charge is different. So X minus 6 equal to -4 and X will be +2. Iron is in +2 oxidation state. +2 oxidation state of iron contains 6 electrons, 6d electrons, 5, 6d electrons. And cyanide is a strong field, so they are now going to get paired. So no unpaired electrons are there, N is equal to 0. And in case of the last compound, in which iron is in +2 oxidation state, the water is a neutral and D6 will be there, D6 will be there, and no electrons are going to get paired since it is a weak field. So the number of unpaired electrons is equal to 4. So 4.90. So you can match, right? So A4, B1, C2 and D3. So option A will be the correct answer for this question. A will be the correct answer for this question. So students, you can able to follow me, right? If you're not able to follow or if you need any help in between or if you don't know anything in between, just put it in the chat box, okay? Don't hesitate to ask your doubts. We are here to clear your doubts only. Got it? Shall I move on with question number 14? Shall I move on with the next question? Shall I move on with the next question? Shall I move on with the next question? Yes? Yes. Question number 14. Which of the following complex has the possibility to exist as meridional isomer? So which compound will exhibit meridional isomer? Meridional isomer and facial isomer. So the FAC isomer and MER isomer. MER is nothing but your meridional. So these two isomers exist in the octahedral complexes which have young A3B3 type. They exist in the octahedral system which has young A3B3 type. Right? So you can see in option A it is young A2B2 type. Metal is platinum and 4 ligands are there. And here metal ethylene diamond. So it is a bidentate ligand. So it is young A2 and B2. And coming to the next option, it is metal. Again, ethylene diamond is bidentate. So let me write AA3. And the last complex is having young A3 and B3 type. Okay. So the meridional isomer exists in compound D. So option D will be the correct answer for this question. Okay. So let me go with one more last question for today's class. 15th question, the last question for you for today is the set which does not have ambidentate ligand. So what are ambidentate ligands? They are the ligands which have more than one donating site or more than one coordinating site to the central metal atom. But at a time only one center can act as a donor site. At a time only one atom can act as a donor site. Okay, but they will have two different donor sites. Like in case of linkage isomerism, we have seen on example, right? NO2 and ONO. In the first case, nitrogen was acting as a donor site. And in the second complex, oxygen is acting as a donor site. So those are ambidentate ligands. So you have to check for the ambidentate ligand. Ambidentate ligand should not be present in your set. You have to find that kind of set which does not have ambidentate. So NO2, in the first option, we have oxalate, NO2 and NCS, in which NO2 and NCS, they are ambidentate because one is NO2, the other one is ONO. And in case of NCS, its pair is SCN. So sulfur is also a coordinating site and nitrogen is a coordinating site. They are ambidentated ligands. And in option B, when you come, it is oxalate and ethylene diamine and H2. Oxalate is not an ambidentated ligand. Ethylene diamine is also not an ambidentated because nitrogen is the only donating site there. Okay. And in water also only one donor site, which is oxygen. So compound option B doesn't contain ambidentated ligands. So that is the correct answer for this. Let's check with C and D also. In C we have NO2. I told you NO2 is an ambidentated ligand. So one of the ambidentated is present there in the set. So that cannot be the answer. And option D also contains NCS, which is an ambidentated. ED2 minus is not an ambidentated ligand. NO2 and NCS, these two will be the more famous or most important ambidentated ligands which we study. Okay. So compound B, option B doesn't contain the ambidentated ligands. Got it? So I hope the questions which we have discussed in today's class, they are very helpful for you. And go through the coordination compounds lesson again. So in the next session, we can solve questions related to crystal field theory and the color of the complex and metal carbonates topic. Okay, we'll cover those things and then we will move on to the next. Clear? So if you have any doubts, students, you can put it in the chat box. Otherwise, you can leave. Thank you so much for listening to the class today. So meet you all in the next session. Okay. Take care. Thank you. Bye bye.